the math, I decided I'm going to start off talking about something today which I did not include on the calendar or in the homework, but I decided it was important enough that I'm going to talk about it, and in fact even added some homework problems related to it, although they're from the supplement, so you don't have to actually turn them in, but you should still know it. And that's because it relates to the fundamental theorem of calculus, which again, love these theorems where the word fundamental is in the name of the theorem. It's probably a hint that it's kind of important. This one's useful. So let's start off with the fundamental theorem of calculus, which would be S4, supplement section 4, fundamental theorem of calculus. Sorry, did I say calculus? I mean algebra, not calculus. The fundamental theorem of algebra is what I've been meaning to say. There's also I think there's a fundamental theorem of arithmetic too, actually. Okay, so this one is the fundamental theorem of algebra, and what does it say? It says, in words, it says you can completely factor any polynomial. So the reason we had to learn complex numbers first is that you need them to fully state this, and here's what it is. So let p of x be a polynomial, so you'll have maybe some constant term, an x term, an x squared, all the way up to x to the n. That's a general form of a polynomial of degree n. Then we can totally factor it into terms x minus ri, right? Where the numbers, the ri's, there's let me say for I equals 1, 2, up to n. So where the ri's are they're the roots of this polynomial, and we are now allowing them to be complex. You need to allow complex ones in order to make this statements. So in general, the ri's are the in general complex roots of p. And if you don't remember what a root is a number that if you plug it in, you get 0. So p of ri is 0 for I equals 1, 2, up to n. So writing this out, p of x can be written as a product of all of its factors, right? So we'll have a x minus r1, x minus r2, all the way up until the last one, x minus rn. And there might be some constant here in front. Okay, so that's the fundamental theorem of algebra, that you can totally factor a polynomial into linear terms. And if you did not allow for complex numbers, it wouldn't be true, right? Like we can all think of, say, quadratic polynomials that you can't factor, at least you couldn't until you learned about complex numbers. So notice why we need complex numbers here. So, for example, if my polynomial was just the simple quadratic x squared plus 1. Without complex numbers, you cannot factor this anymore. You're done. We would say this is irreducible. So since this does not factor over the reals, we would call this irreducible. I'm going to use that term later on today. I'm going to come back to the property of polynomials being irreducible. So that's what it's called when you can't factor it with real numbers. But now that if we allow for complex numbers, we can factor it. And that is, I don't know if you guys know this already, but it factors as x plus I times x minus I. Go ahead and check this if you don't believe it. It actually looks kind of like like a plus bi times a minus bi. Oops. Is equal to a squared plus b squared. You might remember that formula. So you can see this does factor into linear factors. And now that we're allowing ourselves to do that, we can now fully factor every polynomial.
Real quick question.
Mm-hmm.
It's a complex number.
What's a complex number?
Yeah.
A complex number is something of the form a plus bi, where a and b are real numbers, right? Just numbers. I is the square root of negative 1.
Negative 1 or just negative number 2?
It's the square root of negative 1. Were you not here when I did the complex numbers lectures? What was it like? Oh, that was the day before. I started that on the Monday before the midterm.
Yeah, so I did the midterm review, then I left to study for the midterm.
Yeah. Should you can watch the video cast of it then. I do all the complex numbers review. And I'd like to say I feel that your pre-calculus teacher didn't quite do their job, because they should have taught you guys that. But I've noticed, because I just taught pre-calculus before during the winter, and I deliberately made sure to teach them complex numbers, but I noticed not every pre-calculus teacher does that, but I think they should. I really think they should. All right. So a bit of terminology here. I did not specify that all of these roots have to be distinct. Like some of them could be repeated, actually. So if some of these are repeated, we would say that root has multiplicity. So let's see, how should I say this? If some of the factors x minus ri are repeated, let's say, m times, then we would say ri is a repeated root with multiplicity m. Okay, so we're going to come back. We're going to have to use this terminology a few times. Like, for example, i.e., if p of x is, let's say, x plus 1 times x minus 1 squared, or how about, let's say, x minus 7 squared, then 7 is a root of multiplicity 2. It's a 7. Okay. I've been talking about polynomials so far today. Polynomials are a special case of a more general type of function known as a rational function. So now let's consider rational functions, which just mean one polynomial divided by another polynomial. So it'll be a polynomial on top and one on the bottom. So these guys are both polynomials. And we have a special name for the roots of the bottom. And we have a special name for when the bottom has bigger degree than the top. So if the denominator q of x has larger degree than the numerator p of x, then we call the rational function proper. I need to define that because I'm going to have to use that. I'm going to have to use that word a few times in the lecture today. So you might recognize, like, proper is what you get after you do polynomial division, like as far as you can go, right? Like, you remember, if you want to do polynomial division, you can only go so far, and then once you have a remainder with a smaller degree than the denominator, that's when you have to stop. So, like, those are the guys that we call proper. In other words, it'd be like you already did a long division, and we're just looking at the remainder here. So I'll show you more about what I mean by that. But I also should define poles. So any roots of the denominator q of x are also called poles, which kind of makes sense. Like, for example, 1 over x minus 3, if you graph it, it looks like this. It looks kind of like it has a pole, right? Like it shoots up like a pole. Like, I don't know. That's my guess for where the name pole came from. You tell me if you know a better one. But it kind of helps to visualize it. So 3 is a pole in this example. So good. Now I'm ready to do like the main topic of today's lecture, which is so-called partial fractions, or partial fraction decomposition, or partial fraction expansion. So what are partial fractions? Well, let's say I wanted to add two very simple fractions like here. How about let's add 1 over, how about x plus 1 plus 1 over x minus 2? Well, if I want to combine these into one fraction, let's do a common denominator. X minus 2, x minus 2. So I'll get x minus 2 plus x plus 1 over x minus 2 times x plus 1, which is the same as, what is that, 2x minus 1 over x squared minus x minus 2. So that wasn't that hard, right? Like, we've all added fractions before. Is that what partial fractions is? Kinda. Yeah, but in reverse. So the question that we have to deal with now in this class is, what if I gave you this to begin with, and you had to work backwards to get to the original expression, which was just this guy? That's what the method of partial fractions is for. So let me first state it, and it's going to look kind of confusing, but then I'll do an example and you see what I mean. So the method of partial fraction decompositions, which I will just call PFD for short. Or sometimes people just say partial fractions. So let's start with the simplest case, which is a proper, let f of x, which is p of x over q of x, be a proper rational function. And furthermore, I don't want any repeated roots in the denominator. We'll get to that eventually, but for now, no repeated roots in the denominator. Right, so then, according to the fundamental theorem of algebra, q of x can be written as maybe some constant times x minus r1, x minus r2, out to x minus rn, where this is the degree of q. And when I said no repeated roots, none of the ri's are the same as any of the other ones. Okay? Each one of these terms is distinct. Then, f of x, which is p of x over q of x, can be written as some number over the first plus some other number over the second root and plus some other number over the third one. So in this example that I did right here is kind of like, if this was my f of x, we were able to write it as, well, we factored the denominator, which factored as x minus 2, x plus 1. And then we were able to rewrite this as 1 over one of the factors plus 1 over the other factor. And I'll show you how to do it now. I just told you that you could do it. I haven't actually showed you how to do it yet. And I think it's kind of best just illustrated with an example. Yeah, I mean, the way that you do it is you clear all the denominators and you equate coefficients, because you'll have polynomials on the left and polynomials on the right. Okay, so let me just say that. So the numbers Ci let me just say, by clearing the denominators, that means multiplying everything by the least common multiple of the denominators. And equating powers of x. Now, I said this was going to be a little bit confusing until I just did an example. So that's exactly what I'm going to do if this is confusing. And then you'll see the example, and you'll be like, oh, yeah, that's not that hard. So let's do an example of, how about if f of x is 1 over x squared minus 1. Okay. Now, the first thing that you would need to do in one of these problems is, if the denominator is not factored yet, well, then you have to factor it. So that's the first job, is factor the denominator. X squared minus 1 is x plus 1 times x minus 1. So 1 over x squared minus 1, according to what I told you here, can be written as some number over x plus 1 and some other number over x minus 1, right? So what I'm saying here is the same thing that I was saying right here in the context of this example. And now we just need to find out what the two constants are, C1 and C2. So I will now do what I was trying to describe in words right here. So clearing denominators, which means I'm going to multiply everything by the denominator, right? So multiply everything by x plus 1, x minus 1. And what we'll get is, well, on the left, we'll just get 1. On this term, the x plus 1s will cancel, and we'll get a C1, times x minus 1. And then here, the x minus 1s will cancel, and we'll get a C2 times x plus 1. Does that make sense? Everyone got that part? All right. So let's just distribute this out. 1 equals C1x minus C1 plus C2x plus C2. 1 is equal to, okay, now I'm going to collect powers. Before I can equate powers of x, I need to collect them. So that's C1 plus C2 times x, and then plus C2 minus C1. By equating powers, I mean, this is a general thing you can do with polynomials. If you ever have one polynomial equal to another, the only way that that can be true is if all the coefficients match. Now, there is no x term on the left, so what has to be the x term on the right? We don't see an x term here, so that means this coefficient must be 0, right? So that gives us one equation. C1 plus C2 is 0. How about the constant term? What does this have to equal? 1, because the constant term on the left is 1. So the constant term on the right. Okay, so C2 minus C1 is equal to 1. Okay, well, let's see. Apparently C1 is minus C2. So C2 minus negative C2 equals 1. 2C2 equals 1. C2 equals 1/2. And C1 is minus 1/2. Cool, okay. So I figured out what my constants were. So 1 over x squared minus 1 is apparently the same thing as a negative 1/2 over x plus 1 and positive 1/2 over x minus 1. So that's a partial fraction decomposition. Pretty simplest one. Yes?
Are you okay with us just putting the denominators for each one and then isolating one of them for like the x and then solving it? And then, like, you know what I mean? Like, for example, where 1 equals C1 x minus 1, what if you just make that x equal to C1 a 1 and go down from the 0 on?
Good. Yeah. Yes. So you're talking about a shortcut. Yeah. So that's a good little shortcut, and I'll show you guys that. So let me show you now. Actually, what was Robert?
Yeah, Robert.
Yeah. Okay. So let me show you now what Robert was talking about, which is basically it's a shortcut to avoid having to do this equating powers of x thing, and it's pretty nice when it works out. And it will always work in this case where there's no repeated roots. The problem is it doesn't quite totally work when there are repeated roots. It still kind of works, like it'll give you some of the answers. But if there's no repeated roots, then we can do the following shortcut. So let me write this down. So here's the shortcut is applied once we get to this expression. So let me rewrite that expression, which was 1 equals C1 times x minus 1 plus C2 times x plus 1. And the trick is to plug in some carefully chosen values of x that make some of these terms disappear. Like Robert said, if you plug in x equals 1, then this term just goes away. And we can get C2. So yeah, we're plugging in exactly the roots. So plugging in x equals 1, I get 1 equals C2 times 2. Right? Because if x is 1, then this term just vanishes when x is 1. And if I plug in x equal to negative 1, which would be my other root, then I'll get 1 equals C1 times negative 1 minus 1. And now this term disappears. Again, that was the whole point of making these choices of of 1 and negative 1 for x. So this is just gone, actually. right? So 1 is equal to negative 2c1. So I get c2 is 1/2, c1 is negative 1/2. Of course, it's the same values that I got using the other method, but this one's a little bit faster and easier. The thing is, like I said, you can't always do it. So note that this will not work as well if there are repeated roots. And I don't say, I said like doesn't work as well because it still kind of works. Like it may give you some of them, you can't use it for all of them. You might still want to use it. You may still very well want to use this trick even if there are repeated roots. It's not going to give you all of the constants. Okay. And I haven't mentioned anything about calculus. Shoot. I haven't mentioned anything about calculus today. Why is this coming up in a calculus class? Must have something to do with integrals, right? Isn't everything we do here is all about like tricks for solving integrals? Someone had their hand up?
Probably because you have to take the integral of the fraction.
Mm-hmm. Yep. That is, yeah, that's right. Okay, let's just continue on with this example. The question is, yeah, like he said, what if we had to take the integral of this guy? So let's suppose we had to integrate 1 over x squared minus 1. Do we have a method to do this? Before learning partial fractions, could we have done this integral? You could try integration by parts, but it would not work out. You would bang it would be a bit painful, and then you'd realize eventually that it's not going to help you solve it. There's no substitution, at least not an elementary substitution that would work. We might be able to with a method, another method that I haven't shown you in this class that we're going to do in the next section. The next section chronologically, which happens to be section 7.3, trigonometric substitution. But short of that, there's no way I've taught you guys yet that would enable you to solve this integral. So in this class, up until now, you should not know how to solve this integral. It's not possible using what we have learned so far. That's where the partial fractions comes in. Because let's use what we just figured out. We figured out a way to rewrite the integrand here. So by the partial fraction decomposition, the integral of 1 over x squared minus 1 is the same as the integral of, okay, so let's just plug it in, negative 1/2 over x plus 1, and then 1/2 over x minus 1. Or, let's break this up. So this is negative 1/2 times the integral of 1 over x plus 1, and then 1/2 the integral over x minus 1. Are these integrals that we can do? Yes. These are both logs. So that's the key point, is we now ended up with integrals that we can do. It's kind of a neat trick. I thought it was kind of cool. So here, I'll just finish this off. we'll get a negative 1/2 log of x plus 1 plus 1/2 ln of x minus 1 plus c. So that's exactly the power of partial fractions. Okay. So now let's start making things harder. I think next I'm going to do repeated roots. Yeah, okay. So far, I still have not done showing you partial fractions. There's a number of complications that can make things kind of hairy. In fact, these problems can potentially just get brutal, like with the algebra involved. I'll show you guys what I mean. So next, now let's do the case that there are repeated roots. So what if the denominator q of x has repeated roots? Right, so let's say that q of x is x minus some first root to some power, x minus some other root to some other power, and x minus some other root to some other power, okay? Where each one of these are distinct, but you can see each one has multiplicity, so R1 has multiplicity m1, right? So Ri is a root of q of multiplicity mi. Then each one of these, each root Ri will contribute the following sum to the partial fraction decomposition. And I'll write it in a second. It's basically like you have to add one term for each power of the root that appears. So the following sum is, it'll be, let's say use b, b1 over x minus ri. And then you'll need a second term for x minus ri squared. And you'll need as many terms as is the multiplicity. So a b sub m sub I, x minus ri to the m sub I. So that's not even the whole partial fraction decomposition. That's just the contribution from one of these guys. And again, this all is like quite messy to explain, but it's not so bad if you see an example. So let's do an example of, what's my example? X plus 1 or x plus 2, x plus 3 squared. So let's do x plus 1 over x plus 2, x plus 3 squared. So first, is this proper? Yeah, right, yeah. The bottom is degree 3, the top is degree 1. This is proper. Later on, I don't even think I'm going to get to it today, but I guess on Friday I'll show you what to do in the case that it's not proper. Basically, you just do long division till it is proper. But so it is proper, so we can apply the machinery that we built up so far today. And we do have a repeated root, the x plus 3 term. It appears twice, right? We've got, so negative 3 is a repeated root of multiplicity 3. Sorry, 2. A multiplicity 2 thing, yeah. So, multiplicity 2. We could also say it's a pole of order 2. So we can say negative 3 is a pole of order 2. So I'm just saying this so you know the terminology. When people start talking about poles of a certain order, they're not talking about, Poland or poles or something. Okay, so they're talking about how many powers of that factor appear in the denominator of the partial of the fraction. And here's what I was telling you here says about this problem. Thus, our partial fraction decomposition of, here, let me call this f of x. It will be, we'll have some number over the x plus 2. We'll have some number over each power of x plus 3. So there will be a term over x plus 3 and another term for x plus 3 squared. So now you can proceed to solve the problem, but before you can do that, you have to realize this is the form of the partial fraction decomposition. Okay, great. So you guys can see, that's what I was saying. That's what I was trying to illustrate right here. So we'll get how when we have repeated roots, you need to have multiple terms in the partial fractions to account for the different powers of those repeated roots. And now we can solve this. Let's clear the fractions and equate powers. So I need to multiply everything by, let's see, I need a x plus 2 here. I'll need an x plus 2, x plus 3 here, and I'll need an x plus 3 squared here. And that will clear all the denominators. So a times x plus 3 squared plus b times x plus 2, x plus 3 plus c times x plus 2 will equal the original numerator, which is x plus 1. Now, if we wanted to do the trick, the shortcut, now you guys will see what I was talking about right here when I said the shortcut kind of works, it'll partially work. So if I just tried to go do the shortcut, let's see what happens. Okay, so let's plug in, how about if x is equal to negative 2, then I'll get a times 1 plus, this goes away, so both of these terms go away, and I get negative 2 plus 1. So a equals negative 1. Cool. If I plug in, the other good number to plug in would be, what is it, negative 3. Okay, so if x is negative 3, what do I get? Then the first two terms disappear, and I get c times negative 3 plus 2 equals negative 3 plus 1. So negative c equals negative 2, so c equals 2. But those are all the numbers I can plug in, right? Those are all the roots. So you see why this the problem that arises is I don't have enough roots to plug in to find all three of the constants. I only got A and C. I still need to get B. So how can we get B? There's still another kind of shortcut. Maybe you know it?
Just plug everything back in, like the 2 into the thing.
Yeah, right. Yeah, so we'll need to do that. And I mean, I can equate powers of x too. It's kind of a pain. There's still kind of another shortcut here. Someone knows it, because someone's done this before. What should I plug in for x? Someone said it. I can actually plug in any number for x. But what's an easy one? Let's just plug in 0. Yeah, so now just pick any easy number, i.e. x equals 0. And what do we get then? So we'll get a times 0 plus 3 squared plus b times 2 times 3 plus c times 2 equals 0 plus 1. Okay, so 9a plus 6b plus 2c equals 1. And now let's use the fact that we already know what c and a are. 9 times negative 1 plus 6b plus 2 times 2 equals 1. Negative 9 plus 4 plus 6b equals 1. So negative 5 plus 6b equals 1. Did I do this right? 6b equals 6. So b equals 1. Yeah, that worked out. I'm a bit taken aback. I got such a nice answer for b. I almost think I must have made a mistake, because usually you get like uglier fractions. But guess I picked a really good example. All right, so we got all our constants. So what is the result? So x plus 1 over x plus 2 times x plus 3 squared is the same as negative 1 over x plus 2 plus 1 over x plus 3 plus 2 over x plus 3 squared is the partial fraction decomposition. And this is now pretty easily integrated. Right? You'll get 2 log terms for these guys. This is a simple u substitution. It's pretty easy to integrate. But I guess I'm out of time, so I'll just stop it right there and pick up on this on Friday.
Sorry, question. Why did you specifically choose to only multiply these by these?
Actually, I just multiplied everything by the least common denominator. So really, I didn't write it. Here's what I should have written there.